So I'm going to talk about job resiliency and application fault tolerance. And first I want to talk about how things fail, why things break. So one of the more popular ways to have a job fail is a node failure. So node failure on our system can be hardware or software. So common hardware things that will take out a node on our cray are a bad piece of memory. There's a lot of little memory sticks in 22,000 nodes. Voltage regulator, very rarely a CPU will fail. That didn't happen too much. More common is software. So if you see on the cray or on an Exceed system, well, the three little letters OOM in any kind of output, that's bad. That's the Linux out of memory manager. And it will kill things. Sometimes it'll terminate your application. Sometimes it'll terminate something else, like a system daemon, and cause various types of node outages. Node failures can lead to larger cascading failures in our cray. So something that's different about our cray compared to like an InfiniBand cluster is with our machine, each node is a functioning piece of the network. So if you lose a node, you lose a little chunk of the network. If you lose 100 nodes, you lose 100 little chunks of the network. So at some point, it can be a bigger issue. We don't see this too much from user codes, but just be aware that running your node out of memory does have the potential to impact others. Different kind of failure that we see, and on a big machine like the cray, I'm using failure in sort of a shades of gray terminology. We don't have, I like to say that our machine is never 100% up nor 100% down. It's somewhere in between all the time. And our failures are a lot like that. We have sort of a range of failures. The network failures are very much like that. So if we get too much communication injection onto the high-speed network, the network can throttle itself and throttle the currently running applications to try to save itself. And if that happens, you'll see notifications in your job's standard error. That can happen because of your job, or can happen because of somebody else's job that's just got a lot of communication. We usually ride through these. But if you see it, you'll get a little message, and then you can look it up on the portal and actively change things with an environment variable to try to work around that. I'll touch on that a little bit more later. Larger network failures can lead to Lustre errors because Lustre is also using that high-speed network. So on most machines in Exceed and Blue Waters, you're using Lustre for both your MPI communications and your access to disk. And then the big fun failure that comes closer to being an actual black and white failure are problems with the file system. So on most systems with Lustre, when there is an outage, a lot of times it's of short duration, and that's what we tend to see on the cray. We can have a server drop out, and it'll fail over to its redundant server that's mirroring it, and we might have 5 or 10 or 15 minutes of interruption. What you see as an application is that I/O will just stop during that period. So instead of I/O failing, I/O will have a longer wait time. So in Linux, we just call this long-term I/O wait. So like a read that should come right back would just appear to sit there for a few minutes. If you have enough wall time in your job, you'll ride through it. You won't really notice. It will cost you a few extra node hours, but other than that, we tend to ride through these. Slow file system can come from network degradation. It can also come from just heavy I/O load on the metadata servers. Half a dozen people running a find command can make for a bad day on Lustre. We have disk failures that you don't even see. They can sometimes slow down performance if RAID units are doing a rebuild underneath our file system. And then we have storage servers that drop out. Again, a lot of times these will manifest as a short duration of a few minutes. My favorite kind of failure is failure of the planet. So in Illinois, we live in a pretty violent weather area. And so if we get in a close-in thunderstorm strike, sometimes we'll take a little power blip on the building. So everything is anchored down and grounded as well as we can, but if you take a lightning strike, 50 feet from the corner of the building, those electrons have to go somewhere. And so that's just life. In the past, we've had little blips with cooling water changeover, spring or fall, but those have become much smoother after year 1 or 2. So during the cooler parts of the year, we'll cool the machine with ambient outside air, and then we switch over to chilled water in the summer. For a system of this size, I think Blue Waters is very resilient. We ride through some fantastic failures that would bring other systems down. We can lose a node, a handful of nodes. Sometimes we lose an entire rack. One complete rack will just fail for some sort of power issue. And the system stays up, and we'll just lose the jobs on that rack. So that's pretty impressive. And it's by design. Also, there are just, with how many drives we have, Jim? 70,000 disk drives? So 88,000 disk drives. I like to compare this to all the cabs in New York City. All the cabs in New York City aren't always running, and neither are 88,000 disk drives. But the machine stays up because of RAID, and we have a team of on-site engineers that are practically on roller skates, changing things out. And we designed a lot of this in. So we had acceptance tests in the early part of our deployment that actually looked at testing the system under duress to make sure that it could ride through these types of things. I'll just show you some of those. So this is more for staff, just to remind us of the kinds of things that we did. We artificially killed jobs or killed nodes in jobs to see what would happen, verified that MPI could restart on an extra node, things like that. This was an acceptance test where we actively triggered kernel panics and node failures and then observed the results. And Cray builds in support for running this way. So some of this is going to be Cray specific now on application resiliency for jobs at scale. So one of the things you can do with AppRun is give it a flag and let it know that it's free to relaunch itself if a node drops out. So one of the big value adds that you get when you buy a Cray is not just the hardware, it's some pretty sophisticated software. SRun in Slurm and MPI run in Vapich and OpenMPI don't have this similar capability. AppRun is backed by a whole subsystem of daemons that's watching and writing herd on the nodes that you asked for as part of your job. And if one of those nodes drops out and you've given AppRun the correct types of flags, then it can just go get the next node, relaunch itself, and if your job's checkpointed, then you'd start up off your last checkpoint. So here's another way of doing the same thing. You can just ask for a couple different app runs. So the first app run would be the actual job. The second app run is sitting there waiting in the wings in case a node drops out at hour 8 on this job with, 1025 nodes. And they asked for 1025 instead of 1024 because they wanted one extra. That thing's going to sit idle. They'll get charged for it. But if this is a 24-hour job, well, this one's just 8, then they've got that extra node waiting in the wings. And if there's a node failure, the second app run kicks off, starts them off their checkpoint, and they're up and running again. There's a little bash loop example at the bottom. When you see the big teams running MPI on Blue Waters at quarter and half and full machine scale, they're doing this. All of them do this. Especially the full machine jobs, they'll ask for 4, 8 extra nodes for a day. So, Craig.
I would just point out real quick that this is a very, very simple example of the bash code deployment, which is great. This assumes that A.out is smart enough to know where its own last checkpoint was and how to find it and how to spool up from the line.
Yeah, don't ignore the comment.
Oh, yeah.
You've got to, we are assuming that you are all grown-ups and have checkpoint built into your code. Yeah.
How does that one extra unit in the
It was scheduled topologically along with the rest of them. So it's not sitting off on the far end of the machine.
So I thought the Blue Water system tracks out into that huge storage anyway. So where does the one extra one?
It'll come from we had the torch we were running through. So you'll note the 3 torch is not completely uniform. We have storage nodes that are
Service nodes.
The service nodes and nodes that take the data from HSN on the cluster. And when you ask for a certain shape, the topology or scheduler will look at shapes in different dimensions with a what we call fragmentation of the system. So while you ask for a nice, what you think would be a nice easy shape, keynote or Gemini and whatever that works out to be, because there's all these interstitials in your lattice, you get a little bit larger one, and that's the size of that largest bounding box would be no more than 15% from what you asked for.
Yeah.
Okay. So it could have an impact, but usually 1 or 2 nodes is a big difference. And normally what we see when the big jobs run, Brian, New York running earlier this year, 20,000, he'll ask for 100, because he's going to run for 48 hours. And normally you see 2 nodes a day fail on the whole system. So if you're running system-wide for 24 hours, you should expect 2 nodes to fail. 10,
Right.
24 nodes for 8 hours, I wouldn't expect any of failure. But if you've been waiting a week in the queue and the job starts, you want it to be resilient and not exit and then see another job or have another job in the queue. So it's more, it seems like overkill, but because you're waiting in the queue, you might, once you get the nodes, you might put them on the thing.
Yep. Now I went out and looked around Exceed, and there is the potential to do something like this with Slurm and SRON, but I could not find any Exceed site that had done it documented. I found one non-Exceed cluster at a different school that had done it, but you've got to pay and license the plugin from Slurm that gives Slurm this same ability. And when Slurm does it, it wouldn't put it in the same shape. It just throws off a handful of nodes way out at the edge, which is fine on most IB clusters. So back to network degradation for a second. If you see balanced injection and notes about that in your output, there are a couple things you can do. One of them is nothing at all. Or you can ask for flags that indicate how you want to react to other people's codes and their impact on your communication. So there's the description of that. I've got quite a variety of ways of indicating that my job is, let's say, not communicating too much. Maybe it's only got a handful of collectives, so I don't mind if other jobs run through me. Or I might have a job that's just very chatty with a lot of point-to-point. So I don't want other jobs scheduling their, being placed where they'll have a lot of network traffic through my part of the torus. And then if network congestion happens, then the Cray has a way of protecting itself when that event occurs. And here's some documentation on that. We like to recommend starting with setting app run balanced injection to be 64. That's kind of a nice starting point. You can set it up and down from that. It's not linear, so just keep in mind that as you move it around, you can get very different behavior in your MPI communications. But setting this allows some large applications to scale out to the full machine if they have hit the network congestion before. So some teams know to set this to a certain value in their app run script, and then when set that way, they won't have any problems on the Cray. So. Yeah, when we see the balanced injection and the network slowdowns, we'll usually find the application and contact you. So for luster errors, I/O errors, and long-term I/O waits, there's not much you can do if an I/O call just stops and doesn't fail. So you're sort of at our mercy at that point. If you've added some little buffer in wall time and you've got an extra half hour in your job, you'll probably just ride through the event and be okay. That said, if we are throwing errors back from certain types of luster problems, then you can try to catch those in Fortran and C. Now, C programmers are pretty aware of this, but to the Fortran programmers in the room, there is a way to do this in Fortran, and you can set your IOStat specifier. Here's a little example from IBM. And so you can catch and try to detect Fortran I/O issues if the operating system returns an error for that call. And then C programmers are used to just doing stuff like this anyway. F error is a very easy way to handle this. You just check it after you've accessed a stream, and if it's set, then something happened, and you can decide what to do from there. Checkpoint your code. We have a nice checkpoint interval calculator on the portal page. Let me zoom back out a little bit on that. Looks like that when you find it. You can tell it how many nodes you're going to run, how many hours of wall time you want, and it will spit back a recommended checkpoint time interval for you. So you'll have a good ballpark feel for, okay, I'm running at this scale, I should drop a checkpoint every 2 hours. So. And then this last one, I have got a way to hack in a checkpoint if you've never done one before in a C code. So my idea here was to use the C alarm function. So here's a little example of that. So you'd set an alarm. So in this example, in main, alarm 2 means 2 seconds hence. So alarm 2 will just return, but then in 2 seconds, an alarm signal will be sent to this application. And then the alarm signal handler will catch that and catch alarm. It'll set some variables and then keep going, and it'll reset the handler so that it can catch another SIG alarm if it happens later. So this could be a way to, come down here in main, and in your main loop you'd be doing something, and if the alarm went off, you'd handle it, maybe set a flag that says, okay, the next time through the loop, we've got a flag for doing a checkpoint, let's do one. So that's just an easy way to think about that.
They could use that for preemptible workloads as well. Signal.
Yep, you can do that for getting preempted. This is a fun little cartoon I found. This is a business cat in Spanish. So I don't know why I thought that was cool, but I just like the look of it. He wanted help from IT. The problem is that he cannot catch the birds that he sees in YouTube. So, and that's a problem for cats. This will all end up on our portal later as part of our tutorials. And so all the links for the various things that I had above are just shown here. So if you need to look anything up, you can read more about it. And I'm good for time.
So the one thing I Ian kind of mentioned what I mumbled, but so we do have the ability to mark a job as being preemptible, and you're able to use what we have set up. In the past, we used to give a discount to someone, we still might give a discount to be preemptible and specify a minimum walk-off time that you can run with, and then a normal maximum walk-off time. And if you don't have a mechanism to checkpoint when you get a signal to terminate the job, so that say the scheduler says, oh, you specified that you can do a preemptible workload, and some other workload of higher priority wants to use your nodes, if you send a signal to that job, your job can receive that signal and accept it and do a checkpoint quickly, and then exit out before the schedule actually terminates the job. And you get a discount for that work, and you backfill in shorter jobs. So some people take advantage of that, because that's a way to do that on Blue Waters, and I think there are probably other sensors that have enabled proper signal propagation from the scheduler, so the scheduler will issue usually like a SIG term before a SIG kill or something like that, so that you have a chance to strap on it and checkpoint, so you don't lose some of that work.
Yeah, because you can catch SIG term. Where are we here? Yeah.
Instead of SIG alarm, you can catch SIG term.
Yep.
Anyway, so those are some advanced things. We have some users, some workloads that use that, and you can take advantage of that on other systems as well.
Yeah, right there in the signal call for SIG alarm, that could be SIG term, and you could have a handler for SIG term, catch that, do your checkpoint.